scope of thermalization, particularly from the theoretical point of view. First, we started with experiments, but then we focused on the theory. We first discussed some early attempts and early pioneering works that led to the, let's say, to the today's understanding of thermalization in isolated quantum many-body systems. In particular, we highlighted the importance of ETH, Eigenstate Thermalization hypothesis. Then in the last part of the lecture, we discussed applicability of ETH in different systems. I also briefly mentioned few-body systems and non-interacting systems because they are different. I didn't have time, and I will not put much focus on other types of special systems like integrable systems, because today I want to complete this story of Eigenstate Thermalization hypothesis, and I would like to do 3 things today. Let's see how time permits, but I think these are the 3 basic things that for all young people in the field, that if you have not yet experienced that, I think it's good that at least once we go through this calculation so that you get this basic understanding why we are referring to ETH and when we talk about thermalization. So as I highlighted yesterday, so the purpose of this lecture is to be very simple, pedagogical, and to understand what is behind, like almost every second paper in introduction when we say ETH is sufficient mechanism to explain thermalization, and then we put references, and then nobody explains to why is this sufficient mechanism. So today's lecture serves for this purpose to explain you that. So I would like to explain you 3 things essentially. The first thing is that in a non-equilibrium time evolution after a quantum quench, why, if ETH is valid, why long time average in the quasi-stationary state of observables in this time evolving state matches predictions of statistical ensemble. That's the first thing. The second thing is if ETH is valid. The second thing is why, if ETH is valid, fluctuations above time average in the stationary state vanish with system size. And the third thing is that I would like to show you how to derive these 2 things, these 2 properties of the Srednicki ansatz based on the random matrix theory approximation. So as I said yesterday, ETH consists, it's an ansatz, statistical ansatz for the matrix elements of observables. It consists of 2 contributions. One contribution is RMT-like contribution that comes from random matrix theory. That is something I would like to derive today. The other 2 things, which are these smooth functions O of E and F of E omega, are those that involve physics, that involve properties of observables, of Hamiltonian, and so on. They are in principle non-universal. There is still some knowledge that we acquired over the years, how they should look in some cases, but I will likely not have time to go into these details. So the purpose here is now to give you these derivations, and of course you are encouraged to ask questions and interrupt me, and any question is good question, and so please go ahead as yesterday without hesitation. Good? Okay. Okay, so so the first question I will address is why validity of ETH implies quantum thermalization. So in particular, the thing that we're going to discuss is why we can say that the time average, so with this bar, I have in mind time average of a observable expectation value in a long time steady state matches expectation value of this observable in a given statistical ensemble. I just put here rho SE as statistical ensemble. What the statistical ensemble I will really have in mind is microcanonical. I will define these things later. So in principle, let's put here a question mark, because that's something we would like to understand. We would like to show that this is indeed the case. And of course, I will also then deal with corrections. Of course, that is not exactly the case if you consider a finite system. Nobody guarantees you that that's exactly the case. There are, of course, corrections. I would also like to discuss what are typical corrections to that. Okay, so what are we interested in? We are interested in quantum quenches, which means that we start with initial state psi naught. So that's the initial state. And of course, the point is that the initial state is not an eigenstate of the Hamiltonian. Hamiltonian is time independent here. So as we discussed yesterday, we are interested in something brutal that we do to our system. We drive it far from equilibrium, but then we evolve it with a time independent Hamiltonian. So H on psi naught is not, let's say, E naught on psi naught. So it's not an eigenstate of psi naught. Okay. As we know, then how to calculate now time dependence of the observable in this initial state? Well, as you learned in your basic quantum mechanics lecture, this is e to I h t. I put h bar to be 1. O e to minus I h t psi naught. That's just a formal expression. So let's say in the Heisenberg picture. Now the standard trick that you do, I mean, I hope you're all familiar with that because you are now already, most of you are already PhD students, so you know how these tricks go. You here insert a basis, eigenbasis. So let's stick with index alpha. Alpha is the eigenbasis of the Hamiltonian. So H on alpha is E alpha alpha. Here you insert another basis, beta, right, which is just identity, of course. And with that, what you end up is the double sum over alpha beta. And then you have 3 contributions here. The first type of contribution, of course, e to minus IHT acting on alpha is, of course, that's an eigenoperator of alpha. So what we have is then psi naught beta. These are the projections. Then we have e to minus I e alpha minus e beta t. And then we have the matrix elements of observable beta O alpha. Okay, let's say that this is this projection. Let's call it the coefficient C, let's say C alpha. That is C beta star. So the only thing I want to say at this level, so please stop, interrupt me if that is too fast, if it's not obvious how I reached that. Yeah, okay. So what I want to say here is that we have here 3 contributions. The first contribution comes from matrix elements of observables in Hamiltonian eigenstates. That's why we are interested in that, right? That's why observable matrix elements in Hamiltonian eigenstates are important. Then we have these phases. Of course, they are there because that's an isolated quantum system, and this is what gives you what gives non-trivial time dependence. And then we have these projections, and this is information of the initial state, of course. Now, how to now deal with that? Well, in principle, we can decompose now this O of t into 2 parts. 2 parts is the diagonal part and the off-diagonal part. Now, if I want to be more careful, of course, all this alpha beta runs from 1 to d. D is for me the Hilbert space dimension. So if we are dealing with a chain of qubits, L qubits, L spin 1/2, this d is just 2 to the L. Okay, so we now split it in 2 parts, the diagonal and off-diagonal part. What is the diagonal part? The diagonal part is the part where alpha equals to beta. So if alpha equals to beta, then of course this is 0, right? And it's much easier because this thing is just alpha going from 1 to d, C alpha squared. And this, let's say this is equal to my labeling is O beta alpha. O alpha alpha. That is the diagonal part. And then the off-diagonal part is, of course, sum over alpha not equal to beta. C beta star, C alpha, e to minus I e alpha minus e beta t O beta alpha. Okay, now here you can already see where I'm pointing at, because this is time-independent contribution, and this is essentially the contribution which is the long time average. Right. So here, this is something that gives rise to non-trivial time dependence, but then at the end, at the end of the day, it dephases, right? So this term should contribute to dephasing. Now, of course, that is not guaranteed a priori, because I'm not referring to any. I want to be general. I'm just writing down some expressions. Now, already here you can see that there is in all these derivations there is a typical assumptions that we do for generic system that doesn't have any special symmetries, and this is absence of degeneracies. This is something I will be assuming all the time in the in this derivation. Now, from here, we can do a step to time averaging. We can do time averaging. Now, again, I discussed yesterday, in which time window do we do time averaging? This is usually the way how we discuss that. It's like, you know, approximate. We say, well, it should be like long enough, not too long, so it's should be shorter than Heisenberg time, but still long enough that all the non-general short time effects are gone. So with time averaging, I have in mind then O of t bar, right? And of course now the time averaging, what it gives us is actually just the first term, because here, so okay, let me be more formal. So with time averaging, I have in mind limit t to infinity, or maybe let's put it tau, so that we don't confuse it with temperature. 1 over tau, integral from 0 to tau dt O of t. Okay, now with the assumption of absence of degeneracies, actually this is a delta function, but the diagonals are not included there. So everything that remains is actually this first contribution. Alpha goes from 1 to d, c alpha squared O alpha alpha. Now, the way how I call it is I say it's time averaging. We can also invoke the notion of ensembles if you wish to talk that language. Then in this sense, we can say that this is a diagonal ensemble, right? So we can say that this is the same as trace O rho diagonal ensemble, where the matrix elements of the density matrix in the diagonal ensemble is just C alpha squared, and the off diagonals are 0. Well, this is the language that is sometimes used in the community, but if you don't like that language, it's also fine. We can just say it's a time averaged long time steady state. Okay, now from here, I guess it's well, this is now the main result. So from here, it's obvious. I mean, we can already get intuition why. When do we expect thermalization? So now, again, I repeat what I've been telling before. This term consists of two contributions. One of the two contributions, it's this contribution, carries information about the initial state. Right? Different initial states, different projections, different values. Another contribution is, of course, just depends on observable and Hamiltonian. It's independent of initial state. Thermalization means that if we are in the same energy, if we do different initial conditions, if we prepare different initial conditions at the same energy, we should have the same result. Here, I'm assuming that the only conserved quantity is the energy. And how can that be done? Well, it's obvious that then this O alpha alpha for eigenstates actually close in energy or at the same energy density should be independent on alpha. Right. So if O alpha alpha can be well approximated with O of E, right? Essentially, this is this thing. I'm here not writing E bar, I'm just writing E. Right? Then the beauty is that O of T bar, O of E here can go out of the sum, right? Because now this E is independent of alpha. So we have O of E times sum over alpha, C alpha squared. And this is, of course, should be 1 because that is normalization. So then this is just O of E. Right? So long time expectation value is independent on microscopic details of the system. It just depends on the energy, of the state. Yes.
What is the meaning of O alpha alpha equals to O of E?
Yeah. Thank you for the question. So here, essentially, I plugged in the ETH ansatz. So at this point, I say, well, okay, if ETH is valid. So far, until here, ETH may be valid or not valid. This analysis is totally general. General, but not very useful because we don't know what the system is, right? But at this point, we say, well, this is now ETH plus exponentially small. This rho of E is exponentially large in L. So these are exponentially suppressed fluctuations. Of course, these fluctuations now I neglected here because I'm interested in properties in the thermodynamic limit. So I just plugged in this part of the ETH ansatz here. And if I do that, then we immediately see that we forget about initial conditions in the long time average.
E alpha, no, is E alpha. Because from this definition, it's like energy is E alpha plus E.
Yes, of course. Yes, thank you. Yeah, too complicated. I fully agree with that. Yes. I mean, I would just wanted to have the same here, but yes, of course, it's E alpha. Yes.
So still depends on this alpha, on this state.
Yes, it depends. That's true. Now, yes. Now, in the next step, I will be more careful, and I will add corrections to that. So this is the first step, the most primitive step where I just replace that with this thing. Of course, there are corrections, and this is now what I will discuss.
His question is that goes back to the fact that you are creating the state in a small energy window such that the various E alpha are all equal to each other, so they you can replace and take it out.
And of course,
that was the question.
Yes, but I think I will address now this because corrections are also important. So yes, one thing is one relevant thing is now to ask about corrections, and another thing is now to say, well, okay, now essentially I have only argued about independence of initial conditions, but I haven't really shown that equals to the, well, it's not hard, but I haven't really formally shown that that's the same as microcanonical ensemble expectation value. Or in particular, as I said, we are interested to finite size differences between the diagonal ensemble expectation value and the microcanonical ensemble. Okay, so yeah. Okay, good. So for this, to achieve that, so let me yeah. So let me do one more step. So here we are interested at the maybe I can add it here. yeah, let me just add a small remark that with E, I will have in mind the energy of our system, right? And now if I express now E in terms of in the microcanonic ensemble, again, I should introduce here sum over alpha, 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 here sum over beta, the projection on all betas and alphas, so that I get sum over alpha C alpha squared E alpha. So that is my energy. You can say that is expectation value of the Hamiltonian in the diagonal ensemble. Okay, that is the energy of our state that we are interested in. Okay, now to understand agreement with microcanonical ensemble or the differences, we have to be a bit more careful. We have to essentially expand now this smooth function around this energy. Because the point is now that this O of E is a smooth function, right? So if that is a smooth function, then we can say the following. So we can say that O alpha alpha is now can be expressed as O of E plus corrections. Now, corrections, let's say it's delta E dO over dE at energy E plus, actually here we need another correction, so 1/2 delta E squared again at E. We have to go up to the second term because that's of course O. We have to go up to the second order in expansion because we'll see that the first term will cancel. So this is O of E plus, now what is delta E? Delta E is essentially E alpha minus E, right? E is the mean energy. E alpha is a given energy of the eigenstate. So that's the derivative O of E plus 1/2 E alpha minus E squared O double prime of E. Okay, now we can be more careful and now we can evaluate that. Now we can evaluate that in the using the corrections. So having that in mind, then we have O of T. So I will explicitly here write diagonal ensemble just to be clear. If I do it in diagonal ensemble, it's absolutely correct. If I do time averaging, of course, time averaging corresponds to the diagonal ensemble up to details of the averaging. Okay, so yeah, so what is that? So I will follow this formula, of course, here. So this is sum over alpha C alpha squared O of E. That's the first term. Plus sum over alpha C alpha squared E alpha minus E O prime of E plus 1/2 sum over alpha C alpha squared E alpha minus E squared O double prime of E. Now, okay, that's, I guess, straightforward. Now, the idea is that this is of course independent of alpha. We can take that out and this guy as well. And here you see, this is now what I need. In this first expression, what remains non-trivial is this thing. Right? Now you can ask me, what is this thing? Well, essentially that's this, right? It's the same thing. So this thing cancel. This is 0. Right? It's just the energy in the diagonal ensemble. So that's why we needed the second order contribution. We need that. Now what is that? Well, that is essentially the width of the Hamiltonian in the diagonal ensemble. So this is then let's put it like this. Then we can say that this is h squared in the diagonal ensemble minus h squared. And this is something that in jargon we can call the width of the initial state. So the initial state has projection on eigenstates, and the extent or the support over which it has non-trivial projection has some width. Of course, I'm now not saying anything how the distribution goes. Typically, these distributions are Gaussian, but they may not need to be. Of course, I'm here assuming that the second moment is a good characterization of this distribution, which implicitly means I'm assuming something like Gaussian. But of course, these are then second order details that I don't have time here to address. But we can call that simply, I will call that sigma squared of the diagonal ensemble. At energy E, of course, right? Because here we are assuming our system is at fixed energy. But the main thing is that we are here expressing corrections in terms of the width of the initial state in the eigenbasis of Hamiltonian. So, sorry, as I'm a bit, that's an overkill. I don't need here time. Of course, if it's diagonal ensemble, I apologize for that. If it's diagonal ensemble, it's just O in the diagonal ensemble. Okay, so this is, here it's the same trick as before. So this O of E goes again out. So that's just O of E plus 1/2 O double prime of E sigma squared of E in the diagonal ensemble. Okay, this is the first result. Well, now I can ask, how about now statistical ensemble prediction? So let's say that we are interested in calculating O in the microcanonical ensemble. So how do we define that? Let's say that this is 1 over n is the number of states in the microcanonical window. Let's say that the sum goes over Em, or let's say E alpha, O alpha alpha. Of course, this E alpha is then belongs to some narrow microcanonical window, goes from E minus whatever, delta half, E plus delta half. So that's the definition of the microcanonical window. Now, you can ask me, the simple question how to choose this window, how to choose this width. That is question often emerges, and then the typical answer is, well, there is no black box in calculations just to set just some number. So typically, the result should be independent of this delta, of this width of the interval. Of course, if delta is too small, you get deviations. If delta is too large, you again get some deviations, but there should be some reasonable values of delta where results are independent of delta, right? So if you plot that as a function of delta, there should be some broad region for some reasonable number of deltas where results don't depend on delta. Now, in actual calculations, what we mostly do is that we simply average over finite number of states, because if you average over finite number of states, which is still large enough, like 200 or 500, it guarantees you that you are at the same energy density, right? Because the spectrum is extensive in L. L is the number of qubits in the system, and then when you divide this by energy density, and if you take a fixed number of states, you are guaranteed that they all belong to the same energy density, which means they belong to the same temperature. Okay, now again, I use the same, again, this expansion here. So the expression is very similar. Right, so this is something that now I replaced. I replaced with the expansion of the smooth function around the energy E. And again, I get 1 over n. Of course, n is then the number of energy eigenstates in this window. Okay, I get 1 over n sum over alpha of E plus now I already know that this, well, okay, I can put it that way. 1 over n sum over alpha E alpha minus E O prime of E plus 1/2 1 over n sum over alpha E alpha minus E squared O double prime of E, right? Analogous expression as before. And now again, the same arguments give you that this goes out of the sum. And then again, 1 over n sum over alpha. E alpha is just the mean energy in this window, which is set such that it matches E, right? So then this contribution equals 0. And here the same. This term goes out. And then what remains here is essentially it's something that we can call, so this expression here then corresponds to essentially second moment of the Hamiltonian in the microcanonical ensemble. Which I call then, in analogy to that, I call sigma microcanonical ensemble window at an energy E. Okay. With that, I can here write my result for the microcanonical ensemble, which is O of E plus 1/2 O double prime of E sigma microcanonical ensemble of E. Okay, so this is now the main result of this first part, which tells you what? Well, tells you that the expectation value in the diagonal ensemble, if ETH is valid, equals expectation value in microcanonical ensemble up to corrections. Now, of course, the question is, what are now these corrections? Well, of course, in principle, we don't know, but I can talk about typical cases. Now, in typical cases is that, well, the first question is, how about this second derivative? Of course, you can have observables in which second derivative is just 0, so then it's even better, because then we should deal with higher order corrections, which are typically even decay to 0 even faster. But second derivative may be non-zero. And so if it's non-zero, when is it non-zero? It is non-zero when you measure them in terms of energy density, right? So this is smooth function. This is a smooth function. Smooth in terms of what? Or let's say scale invariant when measured as what? When measured as a function of energy density. This is the idea, right? So that energy density corresponds to temperature. So different temperature, different O of E, right? So if that does not vanish, that does not vanish in the case, may not vanish in the case when we express this thing in terms of energy density. Now, when we express that in terms of energy density, if this is something that is order 1, then it depends what is the width of the initial state. Now, the width of the initial state, typically in an interacting system, yes.
Density, that's 1 over n squared. Or 2, because it's 2 derivative with respect to the energy. Derivative with respect to the energy is 1 over n derivative with respect to the energy density.
Okay.
Yeah. 1 over n, right?
Yeah, no.
For local addition.
But okay, yeah, good point. What I wanted to argue is that maybe I actually wrote this definition actually wrongly here. So I always had in mind energy density. So the smooth function is invariant of system size if you plot it as a function of energy density. So when you do derivative, all the expansion that I did actually, I had already in mind the energy density. So this is what these are, yeah. Yes. Thank you. Yeah. So I always.
Then that's the variance of the energy density, not the variance of the energy.
Yes, the variance of the
energy density.
You mean this one?
Yeah, I mean the product has to be invariant under the scaling of energy because the first term is right.
Yeah. So the point that I wanted to make is that if this is the energy axis, let's say this is our energy, right? So now the project, of course, we have now many eigenstates here. And the projection, it is what it is, right? We don't know in principle, but let's say that there is some this contribution. Okay. In reality, these are the histograms because these are discrete values. And this sigma measures the width of this distribution. Now, the proper limit, how at least I usually look at that, is that if you now express that in terms of energy density, right? Let's say E alpha over L, then this shrinks to 0 polynomially, and because so if I didn't rescale that with energy density, that would increase typically as square root of L. The width of the density of states in a quantum many-body system with short-range interaction increase with square root of L, right? Because the variance of the Hamiltonian is proportional to L, so sigma goes as square root of L. Right. So when expressed in terms of energy density, then this shrinks to 0 as polynomially as 1 over L. Okay, so this is, of course, you can now see that validity of ETH is the main requirement here, but essentially it's the crucial thing, but it's not the only thing. So I also made another 2 quiet assumptions. One was the absence of degeneracies, and another assumption that I took is the width of the initial state, right? You can, in principle, here conspire and construct such initial state that have width that doesn't vanish. Such initial states, in principle, are possible Now, if you ask me what are examples, I don't know. I think these are examples if you take superpositions of, I don't know, fully polarized up, fully polarized down states in some spin chains. There exist some examples. They're pretty weird, but they exist. But for most initial states of interest, of experimental interest, that is this shrinking of the distribution is valid, takes place. Now here what I highlight is that these are polynomial corrections. Of course, what I have neglected, what I didn't discuss, are these contributions here, right? But I neglected them because they're exponentially small. When you compare polynomial and exponential, you can forget about these exponential corrections. Yes?
I think that I would be right that the same expression for diagonal and macrocanonical ensemble is not really clear from the calculation here, because in my opinion, this should be n times larger, this variance. Because you have 1 over n, and then you express it as a variance of microcanonical ensemble. But for a variance, you would need.
You mean this n?
1 over n squared.
You're talking about this n?
Yes.
Well, this n is essentially, it has a similar role as CL alpha. You can think of them as, but if you want to.
The example with all the C alphas, C alpha squared equals 1 over n between in your window and 0 as well. Yeah. So it's exactly the same calculation that you have, but now C alpha take an explicit form at the end of the calculation. Thanks.
Okay, so okay, that was the first step. Now the second step, let's put it like this. This was point A, which was agreement with between the diagonal ensemble and the statistical ensemble. Now, another thing that I haven't really discussed is then the time-dependent part. So how do we know that actually the diagonal ensemble prediction is the relevant prediction? You can ask me, well, how do you know that the observable, that the time evolution of observable doesn't just oscillate forever? And this is now related to the question B. Which is related to the variance of temporal fluctuations. All right. So again, I think yesterday I have drawn this picture of T So what we want to say, we want to make sure that the system has equilibrated. If the system has not equilibrated, then there is no point to talk about thermalization or agreement with statistical ensemble prediction. But what we want is that we typically want that these fluctuations here, this width of the fluctuations I characterize as sigma t now, that this sigma t vanishes in the thermodynamic limit. Okay, and this sigma t, so the variance of temporal fluctuations, I simply define it as O of t squared time average minus O of t time average squared. So I talked about that yesterday. I didn't really define it. Now I defined it. Now we know from this previous analysis that O of t for us is just O in the diagonal ensemble. So the question is then, what is this then? Okay, now it's 45 minutes. Shall we make a break and then continue? I think we can, right?
It's a good moment.
Yeah, well,
Okay.
you know, always is a good moment.
Yeah.
Yeah, this is something we should then we then continue doing
Okay.
after the break.
So let's take a break for 10, 15 minutes, something like that.
Yes.
The issue is the following.
Our goal is to show that if ETH applies, if the ansatz for the matrix element applies as given there, then the diagonal part makes sure that we have agreement with the microcanonical ensemble prediction of the time averaged observable after a long time. On top of that, we want to show that time average is indeed the meaningful quantity, so that the fluctuations above time average vanish. And the way how we characterize vanishing of temporal fluctuations is through this variance of temporal fluctuations, sigma t, that we define here. So the non-trivial part of sigma t is this part here, because first you have to take the square of OT and then do time averaging. Okay, so this is, again, a similar exercise as I did before. Now, this is O of t that we derived an hour ago. Now, let me go now to O of t squared. This is, of course, then sum that contains, in principle, 4 indices. I denote them alpha, beta, and then let's say gamma, delta. So we have C beta star, C alpha, then we have C delta star, C gamma, then we have O beta alpha, O delta gamma, e to minus I, E alpha minus E beta, T, e to minus I, E gamma minus E delta T. Okay, now the important thing is that because we are going to do time averaging, right? So we will time average this quantity. So again, I assume absence of degeneracies. So we want this term to vanish, but we have to now see when does this really vanish. So I can rewrite that part as, or simplify that part as e to minus I, and then I have E alpha plus E gamma, then I have minus E beta plus E delta T. So whenever these energies cancel, right, then there's no dephasing, and time averaging will not make this term vanish. So in principle, we have 3 options here. So the first option is the case when alpha equals beta and gamma equals delta, right? So that E alpha equals E beta, E gamma equals E delta, right? Then there's no time dependence. Now there's another case, and this is actually the crucial case, the case that will give the dominant contribution. And this is the case when alpha equals delta and gamma equals beta, right? And then there is a third case. I will just put otherwise, right? So the third case is the case where none of these options are valid. And of course, then I assume that, I assume that the gaps, so E alpha minus E beta does not match E gamma minus E delta, right? So there's no degeneracies in gaps as well. That's another assumption, right? Of course, now I know that if under this assumption of no degeneracies of gaps, then this case I will not consider explicitly, because then after the time averaging, so that's this bar, right? This will cancel. Okay, so the only thing I will consider now explicitly are these 2 cases. Right, so I think I can already now write that this is O of t squared time averaging, because the third case is already Gone? Okay, so the first case gives me here, so I only stay with alpha and gamma. So the sum all goes over alpha and gamma. So this is then C alpha squared, C gamma squared, and then I have O alpha alpha, O gamma gamma. That is the first case. Then the second case is sum over, well, alpha beta in principle. So alpha beta, so here I have C beta squared, C alpha, and then gamma is beta. Sorry, sorry, that's delta. Delta is alpha, thank you. And then I have O gamma alpha, O alpha gamma. Beta. No? Sorry, yeah, you're right. Thank you.
The only thing that this sum out will not equal.
Sorry?
So the only thing that the sum out will not equal. Otherwise, this is the cross section of these first two cases.
Yes. So here, okay, let me now, I think I can erase that. So here let's put it like this equals, now the first term, you see these are independent, two sums over alpha and gamma, which are independent. So essentially, two independent terms essentially just give us this, right? So this is O diagonal ensemble average squared, right? So that cancels with this term. And then what we have this other term, sum over alpha, beta, C alpha squared, C beta squared, O alpha beta squared. Okay, so now I can switch to this expression. So we see that this term cancels with this term. Well, I apologize for that. Now, of course, I should be consistent. If I write time averaging, I should just write O of t without diagonal ensemble. Okay, so the only thing that remains is actually this contribution. So the variance of temporal fluctuations is sum over alpha beta, C alpha squared, C beta squared, O alpha beta squared. Now you can ask me what is that? Well, it is what it is. We, in principle, again, have no information about C alpha or C beta because they depend on the initial state. But what we know is that there is normalization. What we know is that we can set an upper bound for that. Because we know that C alpha squared, C beta squared, they are upper bounded by 1. This is normalization, right? Or in other words, we can assume the extreme situation where actually one of these terms is 1 and the rest is 0. So in that case, sigma t squared is lower or equal to the maximal O alpha beta squared. Okay, so this is the second result that I wanted to derive. So what do we learn from that? We learn from that if ETH is valid, and even more, if ETH is valid for all matrix elements, and typically I have this in mind. I do assume that. Sometimes in the literature, there's people use the jargon of strong ETH. Strong ETH means it's valid for all matrix elements. You can use this language if you wish. I'm not using it because I assume if ETH is valid, it means it's valid for all matrix elements. By the way, for those of you who are much younger than me, even for me, even I was young student at that time, but when ETH emerged as a let's say ubiquitous phenomenon in quantum many-body systems, for several years it was not obvious whether that should really apply to all matrix elements or just majority of them. Actually, there were many papers from between 2008 to 2014 where people discussed these scenarios, and actually at least from numerical point of view, I mean, everything I'm saying now is just evidence that we have, mostly numerical evidence. A crucial indicator that actually established that ETH, when it is applied in ergodic quantum many-body systems, it really applies to all eigenstates, is the measure where you measure eigenstate to eigenstate fluctuations of these matrix elements, and then you just take the maximal guy, the maximal outlier, and scale it with system size, and then evidence is that then really, if ETH is valid, it's valid for all matrix elements, which means that even the matrix element that is the largest outlier in finite systems still decays to zero in the thermodynamic limit. If that is the case, then here we are guaranteed that this sigma of sigma t squared, or sigma t as such, shrinks to zero. Okay, so that is important, I repeat, because of this guarantees you equilibration of time-dependent expectation values of observables after quenches. Yes?
Sorry, for this to be true, do you also need the condition from yesterday where it says that these operators, they need to be normalized? Or...
Yes. That's a good point. Of course, here, today I restricted this analysis only to interacting quantum many-body systems where this is essentially exponentially suppressed. So there is some ambiguity when one discusses few body operators versus sum of few body operators. And then it depends what is the polynomial prefactor, how to know, so that the Hilbert-Schmidt norm of this operator is 1. But these are polynomial corrections that here I neglected. Now, if one considers non-interacting systems, I think that was a question yesterday by David, then actually that matters. And then one can argue whether something vanishes or not, the fluctuation vanishes or not, depending also on how you normalize observables. But I want to avoid that because it's like second order question. Yeah. Okay, good. Now, I hope now I have still time, right? To yeah, to now for the last step. Now to argue how one can derive these two contributions to the ETH ansatz. Okay. Okay, so as I argued yesterday, one can, within the random matrix theory, one can invoke an ansatz which is more primitive than the ETH ansatz, than the Srodnicki ansatz, in which this essentially smooth function is, the diagonal smooth function is just 0, f of e omega is just 1, and then there are just two contributions which one can then derive how they emerge. Yeah. Okay. So how does this derivation goes? Well, I have still in mind my Hamiltonian that acts on eigenstates alpha as in that way. Of course, now I assume for these eigenstates to be perfectly random. So this Hamiltonian is then something like GOE matrix, if you wish. And then I'm dealing with observables with an eigenbasis. I denote it I, right? So that's an eigenbasis for observables. Observables, as we know, they are something physical. So this eigenbasis is something we are familiar with, like spin ups, spin downs, and so on. So let's say this is OI, I, right? These are the eigenvalues of the OI are the eigenvalues of the observable in their eigenbasis. Now the crucial object here that I will deal with is the projection. Is the projection of our eigenstate alpha, Hamiltonian eigenstate onto observable eigenstate. And of course, where is now the RMT approximation, the random matrix theory approximation? The random matrix theory approximation is that the average over this di alpha is simply 0. And the average over d im alpha squared is 1 over d. D is the Hilbert space dimension. Of course, there is normalization. So sum over I di alpha squared is 1.
The average.
Well, okay, that's a good point. So the average in principle is over all eigenstates.
So you not have a
Yes.
for the Hamiltonian. The
Yes,
Hamiltonian
yes,
is fixed.
yes. That's a good question. So in principle, I have in mind. So this derivation, to my knowledge, this derivation was I'm following the derivation that is in the review by D'Alessio and Caffrey and Trigolo and Polconico, even though they do averaging over different realization of Hamiltonian as well. I don't think that's necessary. I think if the Hamiltonian is really random and large enough, then one realization of the Hamiltonian will be sufficient. That's my view. Okay, now what is the point now here? The point is here that this Hamiltonian is this coefficient di alpha is a random variable. So what does that mean, right? So random variable, let's say x, right? If that is x, then simply we have, let's say, a variable that is normally distributed with mean 0, right? Mean is 0, then, well, x squared is 1 over d. Now, the non-trivial thing that we'll also need is x to the 4th power, right? Now, here actually it matters. I mean, I haven't discussed that so far now, whether these are now random variables or complex variables. It was not that important. Now here, if we want to be a bit more precise, then it is important whether we are dealing with random or complex random variables, because the expectation value of x to the fourth is then 3 over d squared if we are dealing with, let's say, real coefficients. So let's say that's relevant for the GOE, Gaussian orthogonal ensemble. While if we are dealing with complex variables, then this is 2 over d squared. Then this is the relevant for GUE, Gaussian unitary ensemble. So this is real coefficients. This is complex.
So you assume they're random in Gaussian.
Yes, yes, yes. Yeah, I'm assuming that, yeah. I'm assuming that the second moment tells you all. Okay, of course, I mean, this is a subtlety in the, you know, if you don't want to complicate your life, you can forget about that, whether it's 3 or 2, doesn't matter. But the funny thing is that actually in the real, you know, the interesting thing is that when that was first derived, so that was first derived, to my understanding, in that review. It was never really explicitly written in papers, even though I'm sure some people knew that before, but it was just not written down. Now, the interesting thing is that I'm here dealing with some properties of algebra of random variables, and then I'm talking whether it's real or complex, and you can say, well, who cares? It's in any case RMT approximation. But the fact whether it's 3 or 2 has some consequences that can be tested essentially in any physical Hamiltonians that obeys ETH. And the funny thing is that these 3 or 2 you can really detect. It even exists in physical Hamiltonians. There were many several examples where people have tested that, and you could really show that it's not irrelevant whether this is 3 or 2. Okay. But if you don't want to complicate your life, you can forget about that. The important thing is that this is something over d squared. And it's not 1 over d squared. It's either something larger than 1 over d squared, as you will see. Okay, now the first point, so point 2a, is about the diagonal matrix elements. Okay, now diagonal matrix elements here, I study them as a function, so O alpha alpha is a function of E alpha. Now, the point is, I mean, this is the RMT approximation, that this smooth function is a constant. And if it's a constant, I will just set it to 0, because all the rest is just a shift of identity times a number, which is irrelevant for our analysis. So the matrix elements fluctuate around 0. And what we want to understand is actually the width of these fluctuations. This width we'll call sigma, let's say, diag squared. This is something we're interested in. So, okay, this is now, so how to get that? Well, if we have a bunch of matrix elements, essentially what we do is we calculate O alpha alpha squared minus O alpha alpha average squared. And the average, so when I say average, is then the average over all eigenstates. So 1 over d trace, right? So let's say sum over all eigenstates alpha, sum over all alpha. Okay, this is what we want to calculate, and this is what we can calculate within this approximation that I have given there. I should go now back to black. Okay, the first thing is that, of course, this O alpha alpha is 1 over d trace of O, and this I set to 0. This is now true 0, it's not O, because I just consider trace as observable. This is by definition. There is no physics in there. If that's shifted by a constant, it's irrelevant. So I can always have such constant that they are traceless. Okay, good. Now the important thing is then this term, which is 1 over d, and then trace, right? So sum over alpha going from 1 to d, alpha O alpha squared. Right, so this is, let me be more explicit. So 1 over d, sum over alpha, alpha O alpha, alpha O alpha. Okay, so now why did I introduce before the observable eigenbasis? Well, I introduced the observable eigenbasis so that I can now insert this observable eigenbasis at 4 places. So I insert here the full basis of the observable. Let's denote it I. And then this is sum over I prime. And so on. So this is sum over j. And this is then sum over j prime. Okay. Well, now you see how that goes, right? It's straightforward, but let's do it explicitly, at least in this case. Let's do it explicitly, because then for the off diagonals, the story will repeat. I may be faster because of the time constraints, but let us see how that works. So that is sum over alpha, and then there is a sum over 4 indices I prime, j prime. So what do we have? Alpha I O I prime alpha. Then we have alpha j O j prime alpha. Now, of course, the point why I introduced the observable eigenbasis is that now these are just the diagonal matrix elements that are non-zero. So that is OI delta I prime. This is OJ delta J prime. So then we get 1 over d, sum over alpha, sum over ij, alpha I squared. Then we have alpha j squared. And then we have OII, OJJ. Now here I refer to now this let's say my random variables, di alpha. So this is d I alpha squared. This is d j alpha squared. Well, as you can imagine, I will need that, but I will still erase it so that I have more space. Okay, so how do we do that? Well, typically in such cases, we take this sum out and then we first do the sum over alpha. So this is sum over ij, oii, ojj, and then we have sum over alpha, di alpha squared, dj alpha squared. Okay, that is, I guess, straightforward. Now, another step that is here useful is just to distinguish two cases. Now, I and j are two independent indices. They can be, of course, identical or not identical. So we can split that. We can split that into two parts. One is where I not equal j, oii, ojj, sum over alpha, di alpha squared, dj alpha squared. Plus the contribution where I is equal to j. So I will just write I. Then we have oii squared. And then sum over alpha, di alpha to the fourth power. And I forgot 1 over d. 1 over d. Okay, I think now should be correct. Okay, now here at this point, I mean, so far, I want to highlight that I've been talking about RMT approximation and so on, but I haven't done yet any approximation yet, right? So you can always express observable in its eigenbasis, that's fine. But now the approximation comes, right? Now the approximation is what are now the sums over alpha, di alpha squared. Okay, so this is the last step that is, let's say, rigorous or correct, general. Now, from now on, I will rely on the RMT approximation. Okay, so what is now the approximation? So I will now first deal with this contribution. So when expressing 1 over d, sum over alpha, di alpha squared, dj alpha squared. So I and j are different, right? So that's actually the mean of products of two random variables. Right, so the mean of products of two random variables is just, so this is RMT approximation, is just the mean of, it's just the product of two means. This is now the approximation, right? So this is then 1 over d, sum over alpha, di alpha squared, 1 over d, sum over alpha d j alpha squared. Okay. Mean of product of mean, approximated by product of mean. And now this we know because I already started on purpose, of course, with the 0.2, right? Defining how what are the means of these two guys. So each of them is 1 over d, so that's 1 over d squared. Right? So this is this contribution here. Now the second contribution here, 1 over d, sum over alpha d I alpha to the fourth, we know already what it is, right? It's either 3 over d squared or 2 over d squared, depending whether we're dealing with real or complex variables, right? So let me summarize that. So 1 over d sum over alpha di alpha to the fourth is, let's say, mu over d squared. Mu is 2 for the real coefficients. Sorry, it's 3 for real coefficients. Mu is 2 for complex coefficients.
Shouldn't we have 1 over d squared for integrators?
Sorry, where?
Second to the last time.
This one?
Yeah, those averages, they were 1 over d. We already had 1 over d squared. Right? The first 1 over d and the average, defining the average.
Yeah, it's defining in the average, yeah. So this is, it's the average over this guy. It's a product of averages of this guy and this guy.
Yeah, that's fine. The 1 average, wasn't this 1 over d? Average features. Yeah, it's also spatial about yeah, makes sense.
Okay, well, now I can, I guess, can erase that. Okay, so what do we get? So we get O alpha alpha squared, which equals, now in the first case, we got 1 over d squared, right? Plus sum over I not equal j, OII, OJJ. That is the first contribution. The second contribution is mu over d squared, sum over I, OII squared. Okay, now we are close, but still one more step. So that's 1 over d squared. Now here, again, our idea is to show, is still to simplify that. I mean, that is better than before, but still not good enough. So now I will split now this sum into sum over I, OII, times sum over j, OJJ. Of course, here assuming that I and j are uncorrelated, independent, so I have to subtract the case where I is equal to j because they should not be the same, minus sum over I, OII squared, plus the second term remains as it is, mu over d squared, sum over I, OII squared. Okay, why did I do that? I did that because we started with traceless operators. So this is 0, this is 0. Well, and then what remains? It remains this term and this term. You see, here we have minus, here we have plus. So this is what I told you 10 minutes ago. It's important that this mu is not 1. Okay, that's the important thing. Now, whether it's 2 or 3, we don't care that much. Okay, so this is then mu minus 1, right? This is minus 1. So we have, let's put it like this, mu minus 1 over d, and then we have 1 over d sum over I OII squared. So why did I do it that way? Because at this point, now I want to come back to normalization, right? I've been talking already yesterday about normalization. I said, well, we should care about normalization and so on. You should ask why. So here it enters. So what is this thing? This thing is actually nothing but 1 over d trace O squared, right? And this is for me, this is normalization. So this is what I say, O, this is the norm of the operator. Here I use, essentially this is, in literature, this is called either scaled Hilbert-Schmidt norm, scaled because we have 1 over d in front, or Frobenius norm, right? It's not the other one norm that just takes the maximal matrix element as an upper bound to be the norm. It's the norm really that is the sum over all matrix elements squared. Okay? And now here, so in principle, I can say, well, this is my, well, to be honest, okay, that is norm squared. So that's the Hilbert-Schmidt norm squared. If I want to be general, that is the norm, right? So in principle, whatever observable you take, you have to take into account the norm. Now, of course, we want to simplify our life. So when we deal with ETH, we want to have this norm 1, right? So let me write it now this way. So now we know the answer. So the answer of the sigma diagonal, the variance of the diagonal matrix elements is mu minus 1 over d times Hilbert-Schmidt norm squared. That is the result. Okay, I will stop now for a second just to discuss this result, because I'm already happy that we managed to derive that. Well, depending on time, then we'll do also the off diagonals, but for the off diagonals, it's straightforward once we know how to deal it with the diagonal, so we can be faster. But here, let me just make this comment. Again, I guess I'm repeating myself, but I apologize for that. But I think that's really important, because here we have the message. The message is that the variance of the matrix element fluctuations is 1 over d. Right? So standard deviation is 1 over square root of d. And 1 over square root of d is this term. Right? That is this. Of course, randomness here is already also present. We put it by hand, right? This is by considering this our projections as random variables. Right? So this is the key result. This is what I promised you to deliver. This is what we now derive. And on top of that, we got more insight, because we got another thing that here I call the norm. And now you can simply understand, if we cook up an observable that has a norm that scales with d somehow, well, of course, then we will change the scaling of the matrix element fluctuation. So then, of course, this is slightly my personal flavor, because I'm emphasizing that. I mean, maybe that's not, some people don't find it that important, but I think if we want to really have a consistent definition of ETH, we have to set this norm to 1. Otherwise, it doesn't make sense to compare fluctuations of different observables if they have different norms. Right? Okay. So how much time do we have?
15 minutes.
Yeah, 15 minutes. Okay, good. I'm actually just on track. Yeah. the only thing that remains is to do now the analogous analysis for the off-diagonal matrix elements, which is then O alpha beta squared minus O alpha beta squared. Okay, so here I will not I will be faster because the analysis is analogous. I will not enter into your coffee break. So I will rather leave you as an independent exercise to reproduce that. Let me still here be more careful. What do we have in mind with these brackets? Actually, it's technically speaking, it's not the same bracket as here. Here's the average over all alpha. Here's the average over all alpha and beta, right? So O alpha beta is 1 over essentially all of diagonal matrix elements, excluding, of course, the diagonal. So it's 1 over d minus 1, sum over alpha not equal beta, O alpha beta. Now, using the same analysis as before, you can realize that this goes to 0 because essentially this is the average over product of two random variables that are uncorrelated random variables, and this is 0, right? Because the mean of random variables is 0, right? So what you get here is the average over product of two random variables, which is equal to the product of averages of random variables, and by definition, the average of a random variable is 0. So the average over this di alpha is 0. Okay, and then finally, the question is, what is this average of the off-diagonal matrix elements squared, which equals 1 over d minus 1, sum over alpha not equal beta, alpha O beta beta O alpha. Well, so how do we proceed? We proceed the same as before. So here we introduce identities. These identities are again of the form sum over I, ket I, bra I. So the eigenbasis of the observable is what we introduce 4 times. So that we end up with similar expression as before for the diagonal matrix elements, but here we have double sum also over alpha and beta, sum over I prime, j prime. Well, okay, here I will now jump over one step because you know that here again, I prime is OII delta I prime, just as before, so I will not repeat myself. Right, so instead of sum over 4 indices, I will just write I and j. So it's O I O J J. This is as for the diagonals, but now the different thing is that we have here di alpha squared di beta dj beta dj alpha. Okay, now where does the algebra of random variables now enter? It enters in the evaluation of these terms. So essentially, this is the mean of, right? I can approximate that as a mean of this coefficients di alpha star, di beta, dj beta, di alpha. All right, of course, assuming alpha not equal beta. Now, the question is, when is that non-zero?
The last is J alpha.
Yes, yes, thank you. Okay, I mean, okay, that's just the language. That's still identical, right? That's the way how I define the mean. I just redefined this quantity. Okay, so far, again, as for the diagonals, this is exact. And now I do the RMT assumption. So the RMT assumption is that there is because alpha is not equal to beta, so the only case that will be non-zero is the case where alpha indices are grouped together. So that is di alpha star dj alpha, and then di beta dj beta star. Okay. Now we know that this is here also what we should require is I equal to j. If I is not equal to j, then that will be again 0. So this equals to di alpha squared di beta squared delta ij. Sorry?
If delta ij is not parameter conception, this is exact.
Yes.
Just say by independence alpha equal to beta to the entire sum without substitution this identity so high. The beta will be just identity.
Yeah. Yes, I agree. So the assumption is that the product of 4 variables is the average of 4 variables is a product of 2 averages. This is the RMT assumption. Okay, well, these guys, we know what they are, right? These are 1 over d, each of them. So this is 1 over d squared delta ij. Okay, now with that, actually, now we arrive to the final answer. So let me, so this is O alpha beta squared. So this O alpha beta squared equals to 1 over d squared that comes from this term. And then we have delta ij. So we have sum over I, OII squared. And again, I can say, well, that's 1 over d times 1 over d sum over I, OII squared. And this is again the norm, right? This is again the norm. So I arrive at my final answer, which is 1 over d Hilbert-Schmidt norm squared. Okay. So from that, the last equation I can just write is then I can say if this is the ETH ansatz, then I can write RMT ansatz, which reads O alpha beta equals, well, I will just write it 0 plus Hilbert-Schmidt norm over square root of d R alpha beta. So that R alpha alpha squared, well, the average of R alpha squared is 2 or 1, depending of whether we are in the GOE ensemble or GUE ensemble, and R alpha beta squared is 1. Okay, so this is my conclusion. So this is again ETH ansatz, this is RMT ansatz. And what I can add at the end is that, as I highlighted already before, these 2 or 1, you may find it quite some artificial quantity coming from the universality class of the random matrices. However, the striking thing is that if you numerically test ratio of variances, diagonal versus off diagonal, you should extract this mu, right? This cancels, only mu remains, mu minus 1 remains. And it turns out that at least for certain models that people studied, indeed, you get the right number, even in physical Hamiltonians. Okay. With that, I conclude, and thank you for your attention.
Okay, so we can resume at 4:30.
Yes.
We do at the end, right? About tomorrow. You should have received also an email to remember that tomorrow the meeting is at 10. So I'm not responsible for you. If you don't show, it's your problem, right? Okay, good.
Meeting in the hotel.
In the hotel lobby, 10 a.m. And then we will go to Barafunda.
Good.
Okay.
Thank you.